Section 4.3, linear independence and span of vectors. A set of vectors S, including p vectors, each one is in Rn, is linearly independent if the vector equation, linear combination of the vectors equals 0, has only the trivial solution. Otherwise, the set of vectors is said to be linearly dependent. That means there are weights C1 to Cp not all 0 such that the linear combination is 0. Linear independence implies that each vector in the set is independent of each other. That means that a vector in a linearly independent set cannot be expressed as a linear combination of other vectors in the same set. Okay, let's see example. Determine if the set V1, V2 is linearly independent. Okay, if we are using the definition, we start here. Now, x1, v1, we start with x1, v1 plus x2, v2 equals 0. Then, this left-hand side the same as x1, v1 is 3, 0, plus x2, v2 is 0, 5. Okay, so it is the same as, okay, that's 3 x1, and the second term is 0, and that is now 5x2. So this and that must be 0. So from here, x1 equals 0, x2 equals 0. So we have only the trivial solution. So they are linearly independent. Right? The same you can prove here, but this one is linearly dependent. Okay, again, same way, using definition, x1 v1 plus x2 v2 equals 0. Now we can organize this the left hand side. Okay, x1 v1, so that first entry must be 3x1 plus x2 v2, so it is x2. Okay, how about second one? 0, 0, so we have 0. That must be 0. That means that here, okay, this must be 0. 3x1 plus x2 equals 0. So we can choose here x2 equal, for example, minus 3x1. Then for any choice of x1, if x2 is minus 3 times x1, then this equation must be satisfied. So for example, x1 equal 1 and x2 equal minus 3, then that will be satisfied. So it is linearly dependent because it has non-trivial solution. Okay. We collect the vectors to form a matrix. The matrix equation Ax equals 0 is equivalent to this vector equation. Right? And columns of A are linearly independent. That is the same as here. Here V1 to Vp are linearly independent if and only if. And Ax equals 0 has only the trivial solution. And from definition, you can see it very easily. And that is also equivalent. Ax equals 0 has no free variable. Once you try to solve the problem, the system, the homogeneous system, once there is a free variable, then it has infinitely many solutions. Now also it is equivalent to here, to this statement. Every column in A is a pivot column. So once the free variable is made from non-pivot column, right? So that every column is a pivot column, then every variable is basic variable, and there's no free variable. Columns of A are linearly dependent if and only if this homogeneous equation has a non-trivial solution. And also, equivalently, the homogeneous system has at least one free variable. Again, equivalently, A has at least one non-pivot column, right? Okay. Determine if the vectors are linearly independent. So we'll try to use technique we developed here. So we'll try to make a matrix in collecting these 30 vectors and try to see if there is free variable or non-pivot column. If there is no non-pivot column, so every column is pivot column, then this set is linearly independent, right? So eventually, solving such problem is related with elementary row operations. Okay, we consider these 30 vectors as matrix. Then from here, now, okay, we try to row interchange, but here there is 2. So if we try to apply replacement, probably non-integer computation is needed to avoid it here. Okay, we'll try to subtract this one, and then we'll put the remainder here. There's subtracted, there's 1, subtracted again minus 8, and subtracted and minus 2. Okay, so from these 2 rows we have that, and then here we can put here now that one 2 0 3, and then this one 0 0 minus 1, right? Now we can eliminate this one by using again a replacement. 1 minus 8 minus 2 is the first row, unchanged. Twice subtraction is 0, twice subtraction is 16, twice subtraction, now there's 7, and 0 0 minus 1. This is pivot, pivot, pivot. Every column has a pivot, so the matrix, the columns of a matrix is linear independent, which is the same as that the vectors are linearly independent. Okay? Okay, here, determine if the vectors are linearly independent. Exactly the same way we can do that. Now, look at these 4 vectors as a matrix. Then now we apply elementary row operations, 1 minus 2 and 3 2. So the purpose is to find the pivot positions. Okay, twice addition, there is 0. Twice addition, again 0. And twice addition, again 0. Twice addition, there is 6. And there is 0, 1, minus 1, and 3. If you interchange the last 2 rows, then 1, minus 2, 3, 2, and there is 0, 1, minus 1, and 3, and that is 0, 0, 0, 6. Okay, this is an echelon form, and if you reach at an echelon form, then you can decide the pivot positions. Here we have pivot, pivot, pivot. Okay, this third column is a non-pivot column. So if there is a non-trivial column, then now these vectors are not linearly independent. So it is linearly dependent, right? So we learned it from here. Columns of A are linearly dependent if and only if AX equals 0 has non-trivial solution. Equivalently, the system has at least one free variable, and also equivalently, A has at least one non-pivot column, right? Okay. In the above example, vectors are in Rn and 3, but number of vectors P is 4. As in this example, if P, number of vectors, is larger than the dimension, then the vectors must be linearly dependent. It should be, because in R3, for that one, we can have a maximum 3 pivots, but there are 4 columns, so at least one column must be a non-pivot column, right? And the number of pivot cannot be larger than the number of rows. So here n is 3, but the number of columns is 4, so that at least one non-pivot column must be there. So such a set of vectors must be linearly dependent. Is it clear? Okay. Here. And V1 to Bp are P vectors in Rn. Then the span, we define span. And here V1 to Bp is the collection of all linear combination of V1 to Vp here. That can be written in the form here, linear combination, so that we write in this way: span these vectors is just the collection of every possible linear combinations. Okay, that is a span. Now, find the value of H so that C, here ABC, is in span AB. Okay. So C is in span AB. We first try to understand that the meaning of this one. Okay. Here, C is in span of AB, but a span of AB is collection of linear combinations, so that it must be every the entry, the element in this set is now like here x1a plus x2b shape. C is in span means that is C. So this is vectorization, and now so that it has a solution, then C must be in the span, right? So that the problem is changed into now the question of existence of the solution. Once we consider these two vectors is a metric, and the C is the right side, right? Okay, so we start with the corresponding augmented metric. Here now 3 minus x and 1, first column, and second column is minus x, 4, and minus 3, and here the right side is 9, h, and 3. Okay, so we'll decide h such that it has a solution. Right? Okay, here we interchange here the or we may divided by 3, then that will be here 1, minus 2 and 3, and a subtraction, no, yes, twice addition will make 0, twice addition, minus 12, so that is minus 8, and twice addition, h plus 18 is 0. Now we, okay, we put here first minus 3 and 3, and then to make this one 0, subtraction, so that here this is 1, minus 2 and 3, and 0, minus 8, and h plus 18. Right? Okay. Okay. Yeah. Now, for that one, after subtraction is 0, and subtraction minus 1, and here subtraction will make 0. Right? Okay. So, after changing the row we reach at here, and scaling with minus 1, 1, minus 2, and 3, 0, 1, 0, and now 0, minus 8, h plus 18. We can eliminate this one by adding 8 times of second row. 1, okay, again, twice added, so 1, 0, 3, and 8 times added, that is now, okay, 1, 0, 0, 1, 0 is the second row, and the third row will be 0, and 8 times added, and this is h plus 18. Okay. Now, here, for this augmented system to have a solution, here now, this is 0, it must be 0 also, right? So that h plus 18 must be 0. So in the case, the solution is 3 and 0, right? So h is now minus 18, that one. Then exactly 3 times of a becomes c, right? So that the x1 is 3, x2 is 0 here. So the value h must be minus 18, okay? Okay. Now we'll here try to solve true or false problems, okay? Okay, the columns of any 3 by 4 matrix are linearly dependent. Is it true? Must be true, right? So that there are 3 rows and 4 columns, so that here it can have maximum 30 pivots. Now, so that at least one non-pivot column exists, so that it must be linearly dependent. U and V are linearly independent, and if UVW is linearly dependent, then W must be span in of U and V. Is it true? Yeah, it must be true. Okay, if you start with, for example, matrix of U and V, and that one is linear independent, that means that it makes 2 pivot positions. And if now you add W as linearly dependent, means that there's 3 is making just only 2 pivot positions. So if there are 3 pivot positions, it must be linearly independent. So that means that W must be in span of U and V. So it is true. Okay. 2 vectors are linearly dependent if and only if they lie on the line through the origin. Is it true? Linearly dependent. Two vectors are linearly dependent means that here a vector must be expressed as the other, or once at least one is 0, for example, 0 and a vector v, if it is given in this way, is non-zero, then again, anyway, these two vectors lie on a line through the origin. You may consider line including a v and 0, and then these two are on the line. And over here, 0 is now, okay. Once the 0 vector is there, then, for example, and any x1, 0 plus 0 v equal always 0, so that this vector and another vector, so that you can choose here x1, arbitrary x1, and the linear combination 0, so it is linearly dependent. If two vectors, u and v, are non-zero, but linearly dependent, then it means that here one vector is expressed as a multiple of the other. So they are on the same line passing through the origin. Okay, so it is true. The columns of a matrix A are linearly independent if the equation ax equals 0 has the trivial solution. Is it true? Maybe somebody may say it is true, however, it is false. The homogeneous system has always the trivial solution. Here you have to say that the equation has only the trivial solution. If you put here now only, then it is true. But it has always the trivial solution. And now it can have some other solutions, non-trivial solution, then the columns of the matrix cannot be linearly independent. So the statement is false. Okay, that's the end of the section. Thank you.